So now let us start the second part of that unit 2. Now, as in the last episode, we have I have forgotten to keep the page number 5. So let us go to that DNA nicking agent and binding agent. There are three molecules are there in your syllabus. Those are all metronidazole, dimetridazole, and tinidazole. These are all azoles. Five-membered ring is there. In that five-membered ring, there are two nitrogens are there at the 1,3 relationship. One nitro group is there adjacent to the nitrogen NH actually, and opposite side of the nitro there is one methyl group, and only difference is some chain which is present on the nitrogen. So only because of this variation, one molecule is metronidazole, second molecule is dimetridazole, and the third one is the tinidazole. They are all DNA nicking and binding agent. Means already we have discussed DNA, but they interact with DNA of microorganism and have the capability to cut or break it. Now, metronidazole is anti-protozoal and antibacterial, means like bacteria, one more variety of variation of microorganism is protozoa. Dimetridazole is not active against human, it is a veterinary drug. The tinidazole is for the giardiasis and amoebiasis. These are all waterborne disease and leads to basically stomach upset. Now there will be a common synthesis of this skeleton, and at the last we will only use the three different alkylating agent to get metronidazole, dimetridazole, and tinidazole. Now let us consider the glyoxal that CHO glyoxal plus two molecules of ammonia, because there are two nitrogens are there in those molecules, and acetaldehyde. If they under this is a multi-component MCR, this is in one step we will be getting this mm, skeleton, that is a and with the methyl group. Now the leftover part is the next step. We will try to nitrate this skeleton. So when it is treated, allowed to treat with the nitrating mixture, a mixture of nitric acid and sulfuric acid, then we get the 2-methyl 5-nitroimidazole. When this NH is the number 1, methyl carbon is the C2, that other nitrogen is 3, fourth is unsubstituted, and fifth Pilecki nitro is there. Now we have to bring this is a common up to these two steps are common, and now we have to use the three different alkylating agent to get metronidazole, dimetridazole, and tinidazole. Now if it is treated with the epoxide, and in epoxide otherwise, that is the ClCH2CH2OH, whatever it is, we will get that nitrogen will be attached with the CH2CH2OH. Now that is metronidazole, and the dimetridazole is methyl iodide, means it is N-methylation happens, we will end up into dimetridazole. And the last one is now not the single step but the two steps. Here first it undergoes the reaction with the HBr goes, actually it's a sulfur. Tinidazole is a sulfur organosulfur compound. So it is symmetrical actually. Nitrogen and sulfur between two carbons will be there around sulfur. Two carbons are there, opposite side kethyl group is there. Now when it is subjected to the oxidation by hydrogen peroxide, then it's a sulfone type, it will come. So this is the structure of the tinidazole. Now let us consider the mode of action. The mode of action is already we know they are responsible for breaking the DNA helix. So let us see that is it's a conversion of pyruvate to acetyl coenzyme A, and then that is in one. So yeah, that is a redox cycle. In that ferridoxin oxidized form is gets reduced actually, and again this is a reduced form is getting oxidized. So this is one part of the oxidation redox cycle, and when then it is going back oxidized form of ferredoxin and the reduced form of the ferredoxin. When the so first is the pyruvate to acetyl coenzyme A. In that conversion, its partner is ferredoxin oxidized form. It gets reduced to ferredoxin reduced form. Now it is entering into the another cycle where ferredoxin reduced form is again oxidized to ferredoxin oxidized form, and RNO2 means our drug molecule. Our drug molecule, by using the NADH, it is getting a free radical. By formula it is RNO2H. Now if this RNO goes, then we get the OH dot. And so homolytic cleavage by this, then this is the DNA double helix which undergoes the homolytic cleavage by OH dot, and the DNA strand breaks. So in that way these molecules are acting as the DNA nicking agent. So with this we have finished actually that pending part. Now we will come to the really the part B, where we have the DNA topoisomerase inhibitors. DNA topoisomerase is one enzyme we have discussed yesterday 7 types. So DNA topoisomerase inhibitors are enzyme inhibitors, and the DNA is a strained polymer. It's a double helix, and the ends of the double helix are fixed in space. So when it undergoes the multiplication, then it has to unwind actually. That unfolding of DNA, it is actually on its own. It cannot be done. It is actually that super twist form will be broken by enzyme topoisomerase, and when the work will be over, then repairment of DNA in that locality, in that region, will occur by taking the help of various enzymes. Now we will discuss the norfloxacin synthesis. That norfloxacin, like that lomefoxacin, this molecule already we have done in the chiral synthesis chapter. Here these are all quinolone antibiotic, norfloxacin, lomefloxacin, ciprofloxacin, these are all quinolone antibiotics. So let us see that it starts with that fluorochloroaniline. Para position ki fluorine is there and meta position ki chlorine is there. Now this will undergo the complex formation, condensation with push pull alkene, means that is one double bond, and double bond one side ki electron donating group is there, another side ki electron withdrawing groups are there. These alkenes are called as the push pull alkene, and when it will undergo the condensation with the aniline, then ethanol goes. This OET will go and it will end up into this now aromatic ring, and this alkene double bond, they are combined through the nitrogen, and obviously here one, and it is not N, it is NH. Now it will undergo, we know that it will undergo the cyclization, and that cyclization key, it will happen C double bond O, but the C double bond O, it's a intramolecular acylation, and that C double bond O will be attached with the benzene ring, but it will undergo the tautomerization, and the C double bond O will be converted into the enolic OH, and this is its tautomeric form. So now when it is treated with the ethyl bromide in presence of triethylamine, then N-alkylation, N-ethylation happens, and the ethyl group will go to the nitrogen. After that, when it is subjected to the alkaline hydrolysis, then ester functional group will be converted into the carboxylic acid, And then lastly, we will be having the nucleophilic substitution by piperazine, that the 6-member ring, the 1,4 position, 2 nitrogens are there. So that where it will happen nucleophilic substitution is with respect to C double bond O, that is at the orthopara position, and with respect to this electron donating group meta position ki nucleophilic substitution will happen. So the fluorine will be there in the molecule and the chlorine will go. So we will end up into norfloxacin. This is the structure of lomefloxacin, and this is ofloxacin. These are all antibacterial, but ofloxacin does not have the quinolone moiety, and their synthesis are not there in the syllabus. Now let us consider that another similar type of molecule like norfloxacin, ciprofloxacin is there in our syllabus, and the only difference in the ciprofloxacin is the that alkyl group in norfloxacin and ciprofloxacin. Cipro, it is you remember it is something related to the cyclo to cyclopropyl ring. It's a little indication is that cipro cyclopropyl group is there at the nitrogen, whereas ethyl group is there in the norfloxacin. Now that synthesis is this synthesis of ciprofloxacin is slightly different than what already we have finished by taking the parafluorometachloroaniline and push-pull alkene. Now this compound we have the polyhalo compound, that is there are two chlorines are there, fluorine is there and the acid chloride group is there in the benzene ring, symmetrically substituted, means the 1 and the 4 position are empty, remaining 4 positions are occupied by the fluorine, 2 chlorines and the 1 acid chloride group. Now when it is treated with the again the diethyl malonate, then active hydrogen, that is a diethyl malonate, means CH2 COOET, that what it is called, that HCl goes actually from the active methylene group. CH2 one hydrogen goes, and this chlorine is the most reactive, COCl chlorine is the most reactive, so this C double bond will be attached with the diethyl malonate, so we will get this structure. Now when it will undergo the hydrolysis, then what happens is not only hydrolysis but this is a beta ketoester, so 1 carboxylic acid will go in, under thermal decarboxylation condition. Decarboxylating agent soda lime is not necessary to do this, so we will end up into beta keto acid. Now when it is treated with some triester, that is orthoester, that one carbon if it is attached with the 3 oxygens, so then we will be getting like this. Actually here the condensation will happen, you can make out actually alkene. So indirectly we are creating here the push pull alkene. In norfloxacin we are bringing like this, and then we have done this cyclization. Now here first we have done that push pull alkene we are bringing here. So this is ortho format, is a react and acetic anhydride. So what happens here, that 2 hydrogens, and here actually the it means 2 molecules of ethanol has gone and you have got this. Now later we will do the nucleophilic substitution by cyclopropylamine. So this chlorine, which is nucleophilic substitution, means only this chlorine is suitably oriented, this, so this chlorine will undergo, so this is your ethanol has gone, and then that is that nitrogen will attack, then ACl will go, you will get the quinolone moiety. And now what it is called, the we have to do that last step, means it will undergo the nucleophilic substitution at the chlorine. This chlorine, first is that chlorine has gone and this cyclopropylamine nitrogen has come, and now this chlorine will go and the piperazine will come. So this is the structure of the ciprofloxacin. Here the difference, if it is the ethyl group is there, that is norfloxacin. Here cyclopropyl group is there, this is the ciprofloxacin. Now what is the mode of action of this molecule? This is the transcribing enzyme inhibitor, that topoisomerase. So this is used for the treatment of the TB and leprosy. This is anti-TB and anti-leprosy agent. So now this is the DNA, and the DNA is undergoing the multiplication, that is called as a replication. And when DNA will give that I mean that protein biosynthesis, it will participate in the protein biosynthesis, then if that is, it will give the the amino acid sequence to the messenger RNA, that is called as the transcription, and then it will go for the translation, and it will be having the protein synthesis, biosynthesis will occur. Now the inhibition of transcription, this step will done by the one more medicine, that is one more drug molecule, that is the rifamycin. So with this, so inhibitors of transcribing enzyme means we are entering to the rifamycin, ciprofloxacin, romifloxacin, that is in chiral drug also mode of action is there for this molecule. This is the inhibitors of transcribing enzyme, and the rifamycin is blocking the transcription. Now this is the rifamycin structure. So this all see, we have to remember, nobody can help actually, you try to remember from this part actually, that is a naphthalene moiety, and this in this naphthalene moiety, this is 2 OH, maximum OHs are there, so this is OH is there at the first position and the 8th position, and here beta position, that is a nitrogen ring is there actually here, and that is attached with the down key one ether is the cyclopentane ring ki one side ki C double bond O is there, another side ki oxygen is there, and that oxygen ki ortho position, I mean in between the ether linkage and the C double bond O, that carbon is chiral carbon and has one more oxygen, means this the acetal linkage is there actually basically here. So that acetal linkage is continuously attached with the amide through C double bond O. Here all this naphthalene moiety key, here all the attachment, the top side 3 are there, down side key 3 are there, 2 are empty, here one position is empty, here one position is empty. So these attachments are all here, top key attachments are all here through the heteroatom. So 2 OHs are there, and another one is a nitrogen of amide linkage. Now other than this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's a C14 side chain is there other than C double bond O. If you want to include, then it will become a C15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Including amide, it is 15. Without that is 14, it is there, and here some conjugation is there actually from the oxygen also, this side one double bond is there, here also here 2 more double bonds are there in conjugation with C double bond O, and then in this part total 1, 2, 3, 4, 5, and here 1, 6. The 6 methyl groups are there in this molecule, and this oxygen side chain ki CH2COOH is there. So I repeat little how to remember. This is naphthalene ring, and the top key OH and NH of amide is there. Down Q and 5-membered ring is there. Benzylic C double bond O is there. This side oxygen is there. This C double bond and oxygen is connected with the acetal, and this oxygen is connected with the amide nitrogen through this 15 carbons. Out of them, one is the amide C double bond O. There one conjugation is there. Here 2 conjugations are there. Total this molecule contains 6 methyl groups. 5 are there at the top, 1 is at the chiral center, and this naphthalene moiety key, here the 4th position key oxygen CH2 COOH is there. So this already you know that it's a transcribing enzyme inhibitor, so it inhibits DNA dependent RNA polymerase enzyme by forming a stable complex. This medicine undergoes a stable complex with the enzyme and stops the RNA synthesis, means a messenger RNA. That's why it is what it is called the DNA, I mean transcription. It stops transcription. So this is the partial synthesis of rifamycin, means this is have a rifamycin is have a SV is available in the nature, and this will be converted into, see, this is same to same, the only thing is here the third position. The third position key, here we are prepare if we introducing one aldehyde group to 3-formyl rifamycin SV. Now this formaldehyde will undergo the condensation with some cyclic hydrazine. It's a pyrazine, but I mean that is that nitrogen is attached with that ring nitrogen is attached with the NH2 and water elimination happens. So this is the rifampicin. So now it is lipophilic means it can cross the blood-brain barrier, and it is good medicine for meningitis form of TB, means which affects the one meningitis form of TB which affects the brain. So this medicine can cross the blood-brain barrier and can be used for the treatment of meningitis form of TB, and obviously it will be given by under medical condition. Now next is the drugs interfering the translation process. Translation means which is directly related to the ribosomal RNA and the protein biosynthesis. So this is the erythromycin, that is the macrolide antibiotic. So this is a big ring lactone. It's actually the 14-membered ring. And here you see, if you count, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's a 14-membered ring, I mean macrocyclic lactone. In addition with this, so many chiral centers are there, and you have the top given C double bond O is there. Here DES and the clad are the sugars, but you no need to remember the structure. This abbreviation is okay. DES means desosamine, and the clad is L-clarinose. These are all sugars. Now, erythromycin is a macrolide antibiotic used for the upper respiratory tract infection, means the throat pain, skin infection, and it's a 14-membered lactone. It has 10 asymmetric centers and the 2 sugar rings. You count all these. Here ethyl group is there. These are all chiral centers, and you can understand this. Only one this center is not chiral, and the 14-membered means 4. I mean this is oxygen, so chiral not possible. C double bond O not possible. Here C double bond O is not possible, and this is the CH2. So these 4 centers, keeping aside, everything is chiral, and all the centers, 10 centers are chiral. In addition with these, the glucose, I mean carbohydrate rings are there, they are also chiral. Here synthesis is not there. Directly we will go to the this picture. You know that is messenger RNA has come. So this is the messenger RNA that has come from the DNA by taking the message for how to synthesize the protein and what is the amino acid sequence. Their code and anticode is there. So this is that ribosomal RNA. So here you will be having so like that proteins that amino acids are coming and protein synthesis is going on. So this is called as the 50S subunit, and so this is the ribosomal RNA. There are 2 subunits are there. This subunit is called as the 50S subunit of ribosomal RNA, and this is the growing peptide chain. Amino acids are coming one after another. I have labeled here 4 steps. One is called as A, B, A, and this B, and then C and D, and this is that is the clove type structure, that is the transfer tRNA. So here 3 RNAs are there. That code is there on messenger RNA, and then this is that kitchen where the biosynthesis of protein is happening by joining the amino acids by the peptide bond formation, that is the ribosomal RNA, and the amino acids are brought by the tRNA. So that bigger unit is the 50S and the smaller subunit is called as the 30S. So let us discuss the 4 steps here. What erythromycin is doing and how it is interfering the translation process, which exclusively stops the protein biosynthesis. So this is the erythromycin binds the 50S unit of the ribosomal RNA and stops movement along the messenger RNA. So erythromycin is blocking that thing, 50S subunit. And then tetracycline, these are all is about to come. So at a time I have done erythromycin, tetracycline, streptomycin, chloramphenicol. So this is tetracycline interferes with the transfer RNA anticodon reading of messenger RNA codon. So this place B here, if you cover it, then codon will be covered, which is there on the messenger RNA. So if it covered, then it is not possible for transfer RNA to read this code, and so the amino acid will not come. That is done by the tetracycline. Now this is streptomycin changes the shape of the 30S ribosomal RNA and cause the messenger RNA defect. Last one is the D. So this is the chloramphenicol binds with the 50S ribosomal RNA and inhibits the formation of the peptide bond. So this is the 1, 2, 3, 4. So erythromycin, tetracycline, streptomycin, chloramphenicol, they are all targeting this process of the translation, so that protein biosynthesis will not occur. So this is the chloramphenicol synthesis. Now let us see the chloramphenicol synthesis. So this is the paranitrobenzaldehyde. When it undergoes the Horner-Wadsworth-Emmons reaction, it's a modified Wittig reaction where we will be getting the double bond. So this is the double bond. Here actually it will come with the aldehyde, and then here this is CH double bond CHCOOMe it will form. And then this is the Sharpless dihydroxylation by using the Edimix beta. So Edimix, that third semester we have discussed, that is the dihydroxylation key. Two reagents will be there, but this is a chiral synthesis. One is by called as Edimix beta, another is called as Edimix alpha. So chiral synthesis of chloramphenicol uses the Edimix beta. So the two OHs will come, a double bond key, two OHs will come above the plane. When it is treated with the methyl chloride and the pyridine, then this will go for the epoxidation. And then when the sodium azide means you will be having the nucleophilic ring opening will happen. So it is a more this thing delta positive center. So this azide comes here and the OH will go to the close to the aromatic ring. When it is treated with the PPH3, then this N3 becomes what it is called the reduced to the NH2. And when what it is called the lithium borohydride is a mild what it is called the reducing agent, which ester gets reduced to the CH2OH, where there is nothing happens on the nitro, and then it is treated with what it is called this acid chloride group is there and the dichloro is there. So in presence of DMAP, this is the dimethyl aminopyridine, means pyridine nucleus की fourth position की one nitrogen is there, nitrogen की two methyl group is there. So this is the base, and then you will be having the amide linkage formation. So with this is the chloramphenicol synthesis is over, and I will stop today. In my next portion, next discussion, we will do the immune system. We will do. Thank you.